Hi, I'm going to present a joint work with Valerie Gutierrez and Juan F. Perez, a model-based filter to improve local differential privacy. So the motivation of the problem is that we want to collect data, but people may not be willing and likely to share their information to a degree. Local differential privacy solves this problem, adding a noise to a data representation of users' values. This addition of noise allows the users to deny any responsibility and protect its privacy. So let's see in this example, we have a client which is Web1 and the representation of the data is 100. Then we add some noise and then we get 101. This information is sent to the server. So an algorithm is epsilon local differential private if the ratio of the probabilities of getting the same output based on two different input values is upper bounded by exponential to the epsilon. I know that this is kind of confusing at the first time, but I hope you can understand with the image I have in the slide. So let's see the first client, see the Web1, and the representation is 100, and the second client is Web2, and the representation is 001. Let's say, just for the second example, I add some noise, I change the bits of each vector with some probability, and then I get the same output, 110 for both of them. What I want to know is the ratio of these probabilities. If the ratio of these probabilities is equal to 1, it means that no matter real the input value, the output, the probability of the outputs will be the same. But the higher the ratio becomes, the probability of inferring something becomes higher, of course, the lower the privacy. And then this information is sent to the server. So in the state of art, we have some several methods to improve. So we have local hashing. We can reduce the collision between the data representation of the users. We can use Hadamard transform, to reduce memory size. And we are sending information to the server. We can use also domain size reduction. We can use Bloom filters, which is a vector representation of the data, or cone sketch, which is a matricial representation of the data. We can also do some post-processing techniques just to clean the estimation counts. So what we propose is that because of the nature of the problem, the algorithm can sometimes add too much noise to some specific values. And when we try to estimate it, it harms the estimation process. So what we proposed to create a filter that removes excessively noisy observation at the server. The pre-filter does face a binary classification task. That is, we want to use a learning model that can predict if an encoded value V is similar to any of encoded version of the expected values, or if instead it can be considered as a noisy observation. To this end, we build two sets. The first set is a vector generated by the Bloom filters, or the expected values I expect to see, of the encoded value I expect to see. And the other set comes from the vector generated from the Bloom filters, where I change HB to 1 with some probability. This probability adds some noise. So now that I have this model that can differentiate if an encoded value is one I expect to see, which I know this value I expect to see, then I can put it on the pipeline. And when I get a value, this pre-filter should be able to discard highly noisy observations. So in the results, we evaluated this solution on two data sets. The first one comes from a SIP distribution with a domain size of 100 and a subset composed of 100,000 of users. We also consider another data set, which is diabetes data, which comes from a diabetes health risk factor indicator from the CDC, and this evaluates the relation between diabetes and risk behaviors of health. This data has about 250 and 250,000 surveyed Americans, and we consider 100 experiments for both of them. So we use the same setup. We use two hash functions. The range of this hash function is equal to 128. The added noise is 0.7, and the threshold to discard any noise observation is 0.8. This means that if the pre-filter predicts higher than 0.8, then it's considered as no noisy observation, and we pass it. But it's lower, then it's discarded. We can see a reduction in the mean square, mean standard deviation, and mean and the standard deviation of the mean square error. We see first in the first filter a reduce about 27%. And we also introduce a second filter, which reduce a bit smaller, the reduction of the mean square error about 3% more, led us to 31% reduction of the mean square error. We also see the impact of the noise probability. So the higher the F, which tells about the noise we are adding, the better it works, this prefilter. It works very well on the SIP distribution and also on the diabetes data. We can see it works as more noise I add, the filter works better. So just a discussion, the benefits are actually mostly with a single prefilter. When we add a second prefilter, it led us to further improvements, up to 30-hour reduction in the mean square error, and benefits are larger when the noise F is larger. This means we have higher privacy budgets. For further work, we have to see the impact of different parameters, the number of hash functions, the size of the vectors, how much noise I will add to the prefilter training. But this method works only very well with moderate values of domain size. We have to see alternative methods are maybe necessary when the domain size is large. Just want to finalize with a wrap-up. Just what we propose is to add a learning model prefilter to discard noisy observations. These prefilters improve the estimation step. The prefilter is based on a pre-trained deep learning model, and we can see that we can reduce the mean square error up to 31%. And benefits are larger when the noise F is larger. This means that we have higher privacy budgets. So we can guarantee more privacy and get it better, accurate estimations. So just to finalize, we can get a value, we can add some noise just to guarantee privacy, and then we have this prefilter that will help us to discard noisy observations. Thanks.
Thank you, Miguel.